Welcome to the Kernel of Truth. Today we're going to focus on calculating the determinant. In a next video, we're going to be looking at geometric properties of the determinant. Today we're just focusing on the numerical quantity. So determinants can only be found of square matrices, and we remember a square matrix is a matrix where the number of rows and columns is the same. So say we're presented with a 1-by-1 matrix. We'll call this matrix A. The determinant, which is notated with vertical bars, like absolute value bars, for a 1-by-1 is just the one number in that matrix, which in this case would be 1. Obviously not a very helpful number, but as we get larger matrices, it will become more useful. In the 2-by-2 case, we'll call this matrix B. And we'll give it 4 numbers, A, B, C, and D. The determinant of this matrix is going to be the product AD minus the product BC. So a lot of times people like to think about this as one diagonal of the matrix, AD, subtracted from the opposite diagonal, BC. Let's take a look at doing a 2-by-2 example of a determinant. So say we're given the matrix B equals 1, 0, 2, 3. The determinant of B would be 1 times 3 minus 0 times 2, for a total of 3 minus 0 equals 3. So now what we're going to do is determine the determinant of a 3-by-3 matrix. So I have my generic matrix M, A, B, C, D, E, F, G, H, I. So the method we're going to use to find 3-by-3 determinants in actually any matrix of size 3-by-3 or greater is going to be called cofactor or Laplace expansion. So we take a look at the first number in the first row and first column. We're going to imagine that all the numbers in its row and column don't exist anymore. So we're going to take that number and multiply it by the determinant of the remaining 2-by-2 matrix, E, F, H, I. Next, what we're going to do is go to the second number in that first row and pretend that its row and column does not exist. This time, instead of adding, we're going to subtract, and the remaining 2-by-2 would be DFGI. Lastly, we're going to look at the third number in that row, delete the rest of the numbers in the row and column, and add that times the remaining 2-by-2, DFGH. Unfortunately, we're not done because now we have to compute those 3 2-by-2 determinants. Well, we remember how to do that from our last step. So our final answer here should be that the determinant of M is equal to A EI minus FH minus B DI minus FG plus C times DH minus GE or EG. The 3-by-3 determinant involves a lot of computation. There's a helpful shortcut method in order to compute this determinant more quickly. The first thing you need to do in this shortcut is rewrite the first 2 columns of your matrix next to the matrix. What we're going to do next is look at the 3 diagonals and the 3 diagonals in the other direction. And the determinant of this matrix is just going to be the product of the first 3 diagonals in orange, AEI plus BFG plus CDH. And then what we're going to do is subtract the other 3 diagonals, CEG minus AFH minus BDI. This doesn't look like the numbers or the letters we got in the last problem, but actually, if we multiplied all of this out and combined all the positive terms first and wrote all the negative terms last, you would get exactly this formula. While the shortcut doesn't give us a lot of information about why this formula works, if you're doing a lot of determinant calculations, it can be quite useful. Lastly, you might be thinking, how do I find larger determinants for matrices of size n by n? It happens exactly the same way we found the 3 by 3. You have to break the matrix up into size n by 1 matrices and multiply them by the coefficients of the first row. And the sign of those coefficients will alternate. So we notice we have A, minus B, C, and minus D. Well, in this case, we have to compute 4 3 by 3s in order to find the determinant of the 4 by 4. But remember, each of those 3 by 3s involves 3 2 by 1s. So in actuality, you're going to need to do 12 determinant calculations here. It's a lot of work, and honestly, past 3 by 3, you should probably be finding your determinant using a calculator. Lastly, we're going to find the determinant of this 3 by 3 matrix using both Laplace expansion and using the 3 by 3 determinant trick. So if we're going to use the Laplace method, we need to identify the numbers in the first row. So we first start with 2 times the determinant of the smaller matrix in here, 0, 1, 4, negative 5. Remember, when we go to the next number, it's minus that number, which is negative 3, times the determinant of 2, 1, 1, negative 5. Lastly, we have a 1 times the determinant of 2, 0, 1, 4. Now we actually have to compute all of these 2 by 2 determinants, and our final answer would be 2 times 0 minus 4 plus 3 times negative 10 minus 1 plus 1 times 8 minus 0. Now we have to do a little bit of arithmetic. We get 2 times negative 4 plus 3 times negative 11 plus 8, which would be negative 8 minus 33 plus 8 for a final determinant of negative 33. We saw that that process involved a lot of computation. So again, let's look at how the trick can make that a little bit simpler. We start by rewriting the first 2 columns, highlighting one set of diagonals and another, and then finding the products. So our first product, 2, 0, and negative 5, 0, plus negative 3, 1, 1, negative 3, 1, 2, 4, plus 8. And then we need to subtract along the other diagonal, 1, 0, 1 being a 0, minus 4, 1, 2 is a minus 8, and a minus 5, negative 5, 2, and negative 3 for a minus 30, which is going to equal 0, minus 3 plus 8, minus 8, minus 30, for a total of negative 33, which is exactly what we found using cofactor or Laplace expansion. So again, it's a personal preference which method you like best, but enjoy using both of them, and I think you're going to see that in certain situations one method is more helpful than another. Welcome to the Kernel of Truth, a new linear algebra focused math YouTube channel. Make sure you like this video and subscribe for updates.